Hi everyone. Today we're going to be going over the 2020 AIME 2 question 13. So let's get started. Convex pentagon ABCDE has side lengths AB equal to 5, BC equals CD equals DE is equal to 6, and EA is equal to 7. And so the question asks us that if this pentagon has an inscribed circle, then we're asked to find the area of ABCDE. So the first thing we can do, which might come naturally to us, is first to label each of the tangents to our incircle, and try to find the length of each of these, because we're not really given much about our pentagon besides the fact that it has an inscribed circle. So we might be motivated to try to find the length of each of these tangents. So if we label the tangents at A as little a, vertex B as little b, etc., we can come up with a system of equations. A plus B is equal to 5, which we can see here. We also know that B plus C is equal to 6, C plus D is equal to 6, D plus E is equal to 6, and E plus A is equal to 7. And we know that because we're given each of the side lengths. So from here we can solve for the length of each tangent, and the easiest way to do this might just be to add up all the equations, which will give us A plus B plus C plus D plus E is equal to 15. And now from here we can solve for each of the 5 variables. So let's see. We have that B plus C plus D plus E is equal to 12. So we know that A is equal to 3. We also have that A plus B is equal to 5, so we have B is equal to 2. B plus C is equal to 6, so we have that C is equal to 4. C plus D is also equal to 6, so D is equal to 2. And D plus E is equal to 6, so E is equal to 4. So now, given that we know each of these lengths, let's relabel our pentagon. Okay, now that we've relabeled our pentagon, let's see if we can't find a way to go about finding the area. So the inscribed circle condition might remind us of this formula. The in radius of our inscribed circle times the semi-perimeter of our pentagon will be equal to the area of the entire pentagon. And so we might be motivated to try to find the in radius of our inscribed circle. So let's label the center of our circle, and let's drop each of the radii. And also connect each of the vertices to our center. And because our circle is tangent to each of the sides, we know that each of these are right angles. So a really sort of natural thing to do is, well, if we're trying to find the radius of our circle, what if we just try to do this in sort of the most brutish way possible? And what I mean by that is, what if we take one of these angles, let's call it theta, and say that well, the tangent of theta is equal to 2 over r by the definition of tangent. So we know that theta is equal to arctangent of 2 over r. What if we add up each of these angles, each of these 10 angles, and say that they sum to 360? Then we have an equation of 10 arctangents, which will sum to 360, and this might seem like it won't work, but in fact, it does. So let's go ahead and do that. So the first thing we can do is, we know that these 4 angles are the same, because each of them subtend the same arc of the circle, which we know because the tangents to the circle are all 2. So we can say that 4 times arctangent of 2 over r is equal to the sum of those 4 angles. Next, we can look at all the angles which are equal to 3, or at least have a tangent which subtends those angles which have length 3, and we see that there are only 2 of them, so we can say 2 times arctangent of 3 over r. Moreover, we have 4 angles in which the tangent subtending those angles has length 4. So we can say is equal to 360 degrees. And so we have an equation in terms of r now, and how we would go about solving this is a little tricky, but first thing we should know is that we can divide this equation by 2. And secondly, we might, instead of trying to bash out the sums of these arctangents by putting it into like using the arctan addition formula, we might be motivated to try to use complex numbers, because we have this 180 degrees here. So if we try representing each of these arctangents in terms of complex numbers, or at least the arguments of some complex numbers, then we know that as long as our final complex number has no imaginary part, that is, our final complex number is 100% real, then we know that we'll be done, because 180 degrees has no complex part, obviously. Any complex number with argument 180 degrees will be completely real. So we can say that the arctangent of any number, if our complex number in the complex plane has angle theta, or some, let's call it k over r, then we know that our complex number can be written in the form r plus ki, where this is the real axis, this is our imaginary axis. And so we know that this complex number, the argument of the complex number, and, well, the argument is just the theta that, or the angle that the complex number subtends in the complex plane. So our argument will be equal to this. So now what we can do is take each of these numbers and represent them as arguments of different complex numbers. So we can say that this is 2 times the argument of r plus 2i plus the argument of r plus 3i plus 2 times the argument of r plus 4i. And we want this sum to equal 180 degrees. Now, how do we combine these arguments? Note that anytime you multiply two complex numbers, say with arguments theta 1 and theta 2, let's call them a and b. Well, the argument of the complex number ab, that is the complex number a multiplied by the complex number b, will be equal to theta 1 plus theta 2, which is equal to the argument of a plus the argument of b. So this is pretty much exactly what we want. We're basically saying that anytime we want to add two arguments, all we have to do is take the argument of those two complex numbers multiplied together. So that means that our expression here will simplify down to this. We have that the argument of r plus 2i squared times r plus 3i times r plus 4i squared is equal to 180 degrees. And now, once we're here, it becomes a lot more clear how exactly we're going to go about finding r. Because, as I mentioned earlier, the only way for the argument of this complex number to equal 180 degrees is if this complex number is entirely real. That is, when we write this complex number in the form a plus bi, we must have that b is equal to 0. Because if b is non-zero, then the argument can't be 180 degrees. So all that remains is to expand this product and make sure that all the terms with I cancel out. So now it just becomes an exercise in algebra. So let's see if we can do this. So r plus 2i squared is equal to r squared plus 4ir minus 4. That's this. And let's do this one next. R plus 4i squared is equal to r squared plus 8ir minus 16. And finally, we have r plus 3i. And now, let's multiply these two together so that we have r to the 4th plus 12ir cubed. We have minus 16r squared. We have minus 4r squared, and we also have minus 32r squared. So 16 plus 4 plus 32 will be minus 52r squared. Now we have minus 64ir. We have minus 32ir. And that gives us a total of negative 96ir. And finally, we have plus 64 at the end. So we have this product, and we want this to be entirely real. So the last thing we can do is, I guess we don't have to multiply everything here. We only have to look at the terms which have I and make sure that they sum to 0. So let's see if we can do that. So our highest order term will be we have 3i times r to the fourth, and we also have 12i times r to the fourth, so that gives us 15i r to the fourth. Next we have negative 96 times ir squared, and we also have negative 156 ir squared. So negative 156 minus 196, or 156 plus 96 is equal to 252. So we have 252 ir squared. And finally, we're left with the constant terms, which is just 3 times 64, which is 192 times I. And because we want this expression to be entirely real, we want this to equal 0. So ultimately now we're left with a quadratic in r squared. So let's see if we can figure it out. Well, the first thing we note is that these all have a common factor of 3. So we have 5 times r squared, r to the fourth rather, minus 252 divided by 3, 84 r squared, plus 64 is equal to 0. And now this comes out to be 5r squared minus 4 times r squared minus 16 is equal to 0. And so now we have a pretty easy quadratic to solve. We have that r can be plus or minus the square root of 4/5 and plus or minus 4. Obviously the negative solutions don't work, so we can disregard the negatives. So now we're left to choose between the square root of 4/5 and 4. But note that if r is less than 1, then this picture here, it doesn't really make sense, in the sense that our numbers here are too big, because each of these is like 6, 7, and 5, and we can pretty easily just use our intuition to eliminate this answer choice. We're going to be pretty hand wavy, but given that this is an AIME, it would be pretty easy to eliminate this answer. So we have that r is equal to 4, and now using our original formula, r times our semi-perimeter is equal to a. Well, we know that our semi-perimeter is 15, so we have that our area is equal to 60. And so we are done.